Good evening, everybody. My name is Kevin, and welcome back to the ESP32 product creation journey. We're going all the way from concept to product using an ESP32 and learning a ton of stuff along the way. Hopefully, this process can be helpful to others. I will give the disclaimer that I always give, which is I'm not an expert in all of the things that we'll be covering. I do have extensive experience in many of the things that we'll be covering, but take all of this for value all of this for the price that you paid for it. I guess I would say that. So, what are we working on today? We're going to be looking at FreeRTOS tasks because I need to. And so, but before we do that, a few things that I wanted to cover, kind of tie a bow on from the last stream. The first of which is versions matter. And one of the things that I've run into, if you've been watching the stream for, the last week or so, is that I have been mixed up and flipped around backwards multiple times with esp-idf versions in sample code. So like in almost all of these areas, if we click on a reference here and we'll just say, I don't know, Bluetooth LE, and then find the application example. If you come down here, it'll say, here's an example. We'll open that up in a new tab. We'll come over here, and the first thing that you'll notice is that we are on some, I say random, it's not, but a seemingly random commit of the source. And so this is where you could select and come down and say, I want to go to master, or I want to go to release v2.0, 2.1, 3.0. These are extremely important, and what I have learned just in the last couple of weeks of playing around with esp-idf is don't just blindly click on these from the example without knowing exactly what version you are looking at, because it matters. And an example of that is if we come to, I think it's an API reference. No, yeah, let's go to API reference. Let's go to provisioning. Let's go to smart config. This is what we played with in the last stream. And if we come to smart config, you will find that we need to find the, here it is. The enumeration, the smart config type. You'll see that there's an ESP touch, an air kiss, an ESP touch air kiss, and this ESP touch v2. I was getting hung up because this v2, as I learned after the last stream, is specific to version 4.3 of the ESP-IDF. And for those that are interested, when I was messing around with smart config the last time, I was questioning like, what's the security like? In ESP version 4.2, there is no AES encryption of the credentials as they're being broadcast across your network to configure a device. I'm not going to recap all of what smart config is. You can check out the last stream for that. But in ESP version 4.3, they've introduced ESP Touch version 2, which does include an AES encryption of an option to encrypt those, the SSID and password as it's being broadcast using UDP packets. Now, this is important because I was talking about, well, maybe I'll just rev to 4.3, but since I have decided that we're not going to do that. And the second part of this is in the docs, I have this bookmark. It just comes to latest. And what I've learned is I don't want to do that anymore. I don't want to just be on latest because this is exactly what it means, the latest docs. But I am developing on a certain version of esp-idf. And so what I really want is down here in the versions, I want to select version 4.2, which is what I'm on. And if you look here, you can see pre-releases. 4.3 is still in pre-release. So that is not something that I want to dev on. I don't want to dev on pre-release. If that goes release before I release, I might consider revving to it, but I'm not going to actively develop consumer code on a pre-release version. I can test and play with new features if I need to, but my general rule of thumb for me is be on the latest actual release. And then, as I explained in the last stream, only rev carefully and intentionally. And so if we come to versions here, we can click on stable. And if you'll notice when I do that, the stable version is 4.2, which it's selected for me down here. So those are the same. So what I really want is version 4.2, and I just want the main docs version. Here we go, 4.2. So what I'm going to do is I'm going to delete this bookmark, and I'm going to add it anew. And we'll call this esp-idf docs. So that now when I use my handy shortcut, I'm coming to version 4.2. And if we come into here and say API reference, provisioning, smart config, and we scroll down to that config type, you will see that there are just these three. There is no esp-touch v2. And that's because that's a new feature in 4.3. And so as we were coming through, we've been doing a lot of copy pasta lately. I've been getting tripped up because I'm on 4.2, but I've been in the latest docs, which is linking to latest examples, which is going to be using features from 4.3, which I don't have, and it's led to compilation errors and lots of me chasing my own tail, figuring out what is wrong. And so the moral of that story is versions matter. Make sure you're in line documentation-wise, example-wise, and whatever version of the IDF that you're running. And as an added bonus, like I said, Smart Config version 2 in IDF 4.3 has AES encryption for that provisioning process. Okay. Excuse me. Let's see. What was the other thing I wanted to go? Oh, we've been spending a bunch of time tasting and sampling the different versions of provisioning. Just as a reminder, let's look at that. We played with BLE, total size of 962K. We did soft AP, which was 812K. And then the smart config was all the way down at 718K. I said I was going to make a decision, and I have made a decision. And that is that we're going to go with BLE for now. I just, in considering all the different things and knowing what I know about current customers that have had to use soft AP to configure our puck product, I feel like BLE is the most bulletproof way as well as the best user experience way if I can pull off all of the app stuff that I'll need to. So that's the decision we're going to move forward with for now. However, like I've talked about before, we want to design this in such a way that we can swap it out if we need to. So we're going to go with BLE, and the size is a little bit of a concern. So if that becomes a problem, then our hand will be forced and we'll have to back down to like a soft AP or a smart config. But I want to make that in such a way that I can just make that change and it's not tightly coupled into all my code. So I have to go in and tear and move and refactor a bunch of things. And so as part of that, I came to the very real realization last stream, if you were following, that I am still very much going through the learning curve of FreeRTOS. Now, I would consider myself an expert. I would say expert, very advanced in the particle ecosystem, because this product is built on the particle P1 module, and I have spent years poring over the documentation, finding edge cases, understanding all the ins and outs of the particle ecosystem. And now I'm essentially going through that same process again with esp-idf, which is based on FreeRTOS. And a lot of the particleisms that I got used to don't exist, but the ESP ecosystem has its own nuances and quirks that I need to learn and understand, kind of best practices. And I'm still very much learning that. And so that's one of those areas where I'll hedge and say, like, follow along the journey, but don't take my word as expert final. You should do it this way. And feel free to point out like what I'm doing wrong when it comes to esp-idf and FreeRTOS and things like that. But having said that, I want to, I'm going to just show the process that I'm going to go through, which is I need to spend some time understanding more about FreeRTOS tasks, because that's what all of the flow of a FreeRTOS firmware is based around, is this idea of tasks. And I don't mean for this to be a tutorial. We're going to just play around with some things so that I understand them better. And so The first thing that I've done here is I got rid of all that provisioning code that we had dumped into our main.cpp here. I broke it right back down to the bare essentials. I set up our logger that we created. And right here, I was just testing the documentation for FreeRTOS is great, and you can use most of it, but there are some ESP isms that change the documentation from FreeRTOS a little bit, and I'll explain that in just a second. But they talk about tasks should never be returned from. And so in a lot of the code, you'll see something like this that I've commented out, which is like a while true or a for semicolon semicolon or a while one, an intentional infinite loop to spin forever. But as I was thinking about that, that doesn't always make sense. Like sometimes you might want to spawn a task that has a finite end, like that finishes. Like I'm going to spin off a task to do something like, maybe check the battery level. And I could have a task that's an infinite loop that checks the battery level every X number of seconds, or I could just have a task a task that checks the battery level, returns, and then it's done and it cleans itself up. The reason you would want to do that, perhaps, is because whenever you spawn a task in FreeRTOS, you're consuming memory. It has to create its own stack. I mean, it's truly like a separate process like you would run in Windows or something like that, that creates its own resources and uses memory and things like that. And so if you want to keep it running indefinitely, that's fine, but there's certainly an argument and a use case for, I don't want it to consume those resources forever. I just want it to consume them while it's doing the thing I need and then to clean itself up. And so as I was reading through that, I thought, well, it says you generally shouldn't return from a task, but what if you do? Like, what happens? And a lot of this is just, again, the learning curve of I'm sure I could read and figure this stuff out, but it's just as easy to write some code and play with it. So that's what I did here. You can see, let me make this just a little bigger. That is a big jump from where I was to where I am now. Okay, that was just one increase in size. I'm just going to say info, peace out. I'm going to flush that. I found out that if I don't flush it, when the task cleans itself up, like it never, depending on how the tasks switcher is handling it, it'll never actually print this out. So forcing a flush prints it out. And then I've done a couple things. I didn't have this before. I just returned. I just tested, like, what happens if I return? It says don't return generally. What happens if I do? And the answer was nothing. Like, it just, I was expecting possibly the Watchdog Timer to time out and have it reset, but it really just sat there happily spinning on the main idle task. And again, I don't mean for this to be a FreeRTOS tutorial, but something I learned in esp-idf is if you look at FreeRTOS examples, everything says you can create your tasks and then you run the v task start scheduler or something like that. Like you start the scheduler, which is in charge of giving CPU time to all the tasks. It like switches through them and context switches them. Again, just like a CPU does on a regular computer. And so all of those examples show setting up the task and then calling the start on the scheduler, on the task scheduler. None of the sample code that you'll find from esp-idf does that. And I learned that the reason for that is because it's already called for you. esp-idf calls the start task scheduler before it gets into your code. And in fact, this app_main that we've created, which is like this would be equivalent to, if you're familiar with the Arduino world, like the loop function. This is actually a task in itself. Like the esp-idf framework runs your app main as a task. So you're already, if you're thinking of Inception, you're already one level deep at this point. Whereas in the FreeRTOS examples, you have to create that first level. esp-idf takes care of that. So, and then from in here, we're welcome to spawn as many other tasks as we'd like, memory permitting. So the next thing I tried was, well, what happens if I call vtask_delete with null? And this is the FreeRTOS way of saying, I'm done with my current task. It turns out you can finish a task. Clean me up, like clean up all my resources that I acquired to run and blow me away. Okay, so let me show you what that looks like. And this is the output. I won't run it again. This is the output that you get. This is just normal startup stuff that you see. And right here, again, is the esp-idf framework calling the schedule start for you. And it starts one on the Pro CPU and on the app CPU. Remember, the ESP32 that we're using is a dual core. It has two. Generally, your code's going to run on the app CPU. There are ways for you to say, run this task on the, I think it's program CPU is what Pro stands for. So you can use both of those, but most of the framework stuff runs on the Pro CPU, and you should, if you can, keep your stuff to the app CPU. That's just a general IDF thing. Bellum, welcome. Thanks for joining. Great to have you. Just talking about FreeRTOS tasks. I'm not sure how long you've been here. Maybe you've figured that out already. So that's what happens. We can exit out a task, and again, I was expecting maybe that the Watchdog Timer, for those that aren't familiar, a Watchdog Timer in hardware is just a timer on the device that says, if nothing's happening for a certain amount of time, I'm going to assume you've locked up. In an embedded scenario, that could be very bad. And so a Watchdog Timer says, like, hey, if nothing's happened in a certain number of milliseconds or seconds, I'm just going to restart. I'm going to like restart the whole chip and start it over because something must be wrong. I felt like that could potentially have happened, but it doesn't. It's just happy to blow away our app main task and just keep running that idle task. So right now the ESP32 is chugging along on that idle task and happily not running any more of our code. So that's what happens when we remove a task. One thing I should mention that I've learned through this, and this was obvious to me, but the docs mention it, and it should be clear to everybody. vtask delete does not clean up any resources that you've acquired in the task. So if I were to malloc up here, like create some amount of memory, I need to assign it to something. So like a void pointer memory equals malloc, and then grab like whatever 500 bytes of memory. When I call vtask delete, that memory will not be freed. That would be a memory leak, the definition of a memory leak. So any memory or other resources that you allocate in your task, you are responsible as the task creator to also clean up. vtask delete will only clean up and reclaim the resources that the task creation is part of the framework acquired. And so just something to be aware of. Watch for memory leaks. And so, man, I'm having a shortness of breath. Don't worry, I'm okay. I just I feel like I need a drink. I might have to bail out here in a second to get some water. Okay. So something I want to play with today to understand this stuff a little better is the esp-idf is C code. I mean, this is all of the built-in functions or everything are a C style of coding. And I would like to write, I like to write in C++. And this is one of those like battlegrounds in programming and firmware development of like, the only true way is assembly. The only true way is C. Very few people say the only true way is C++, but as these chips get more and more capable and support newer versions of the C++ compiler, which I believe esp-idf right now supports C++ 14, with I think 17 coming soon. I like the code that we get from C++ better than the code that we get from C. And again, I don't want to have any arguments about why that's a dumb idea if you think that that's the case. I think that the creators of the language have done a crazy good job of optimizing things, and you hear about things called no-cost abstractions where they have optimized these things extremely well, and as much as people like to think they can beat the language writers at optimization, that's rarely true. But that said, do whatever feels right to you. For me and for this project, I would like to go the C++ route. I think we have the code space, and I think from a readability standpoint and code maintenance standpoint, I would prefer to do it in C++. Let's see, Bellum, what do we got here? Small channel design suggestion. Your channel icon is black and white, but the followed sidebar uses black and white to denote offline streamers. So one might assume you're offline unless they actually hover over your pic. You mean, are you talking about my image? Like the picture of my face, like at an angle like this? Is that what you're talking about? Okay. I did not know that. That's a great, like I mistakenly designed my icon to be like eternally offline. Cool. Okay. Yeah, I will fix that. Thank you for the suggestion. I did not know. I'm actually going to write that down because otherwise I will totally forget. We'll say fix Twitch icon. Cool. Thank you, Bellum. Okay. So how does that tie into tasks? Well, I don't want to write this C code everywhere and have this giant app main. I would like to modularize out the code, and you can do that with C. I'm not saying you can't. But what I want to see is how does that work if we want to have like C++ classes, like actual class code, and how can we tie that into tasks? And so let's just play with that a little bit. The first thing I want to do is just to get my feet wet because I've mostly copy-pasted all of this task code, is trying to create a task. Well, I mean, maybe let's just do that as a class. Very simple. I just want to know what the available heap memory is at any given time as we're running through this. And this will serve a purpose later because with some of the like Bluetooth stuff, it uses a massive amount of memory apparently, but I would like to visually be able to see that. And so I would like to, let's just see what we can code up and see what we can get to work. And so I think there is like a task. I'm trying to remember if there's like, well, let's go to FreeRTOS here. Task API. So yeah, task to be created. And then I think it says it in the tasks, the FreeRTOS docs, not the esp-idf task. But anyway, the form for a task is this. So I know I said I didn't want to copy pasta, but there's no sense in writing the shell of this. Okay, so let's call this report heap memory. And so it returns void, so nothing. And then we pass it this void pointer of PV parameters. So we can actually pass context into tasks as I understand it, and then use that context by like, casting it out to whatever we need it to be. And then again, they suggest something like this for semicolon, semicolon, and then putting task code here. Now, an interesting thing that I would be curious is how does that differ from, as far as not really performance, because I don't think it'll matter there, but maybe code size, as opposed to like a while one or a while true. I'd be interested to know, like, is for semicolon, semicolon, does that optimize down a little better? And we could probably check that. So let's just play around. Task code goes here. And so what we're going to do is we're going to come into heap memory allocation. And I believe there is, here we go. We can get it during, yeah, here we go. Via external config. This is allocating, this is freeing, realloc, align, used to deallocate, no. Here we go. Get the total free size of all the regions that have the given capabilities. And I believe if we don't specify it, that's where this malloc cap SPI RAM, like memory allocated, can only be accessed 30. Well, so we can get the free heap depending on the type of memory that we want to look at. Heap caps get minimum free size. So from a memory perspective, if you're new to programming, the heap is a region of memory that you can randomly grab chunks of to assign variables and objects and things to. But it does get fragmented. If you remember the old Windows days, you would have to run the defragmenter every once in a while, because if you have this giant chunk of memory, it's going to grab pieces here and there, and then as you free up those pieces, you'll have a total amount free, which is like every byte in the whole heap that's free. But realistically, because they're spaced out, like you only have these maximum size chunks because you have objects allocated around it. Hopefully that makes sense. And so here we go. Heap caps get largest free block. This will tell you, like, get free size will tell you just how many bytes are available. Oh, actually, let me read the docs because it'll say it better than I can. It says, note that because of heap fragmentation, as just poorly explained by me, it is probably not possible to allocate a single block of memory of this size. Use heap caps get largest free block for this purpose. And so that's, we want both of them. But let's see this. The information returned is an aggregate across all matching heaps. The meaning of fields are the same as defined for this. Okay, so maybe we could just do heap caps get info and then print out a bunch of stuff. Then prints a 2-line summary, so we could call heap caps get info or heap caps print heap. Oh, this is going to auto print it for us. I'd rather just get it and then print it the way that we want to print it. Cool. Dump all, yeah. So I'm not sure which cap we'd want to pass into it. So let's come back up here. Let's call this heap caps get info. And then let's look at, we'll just set this aside here. And we'd have to pass the type for it as well as the info structure for it to populate. But let's see if there's an example, which there almost always is. Finding available heap. I wonder what this will link us to. Which returns the number of free bytes in the data memory heap. This is equivalent to calling, yeah, cat malloc alloc. Okay. Get free size can also be used to return the current free memory for different memory. Get largest free blocks. Returns a multi-heap info structure which contains the information from the plus some additional heap specific. Printf, yeah, so these are all the same things. So we want to call it with malloc cap 8-bit. Heap caps get info. So let's do that. Oh, let's just mess with this. This is where, I'm learning this stuff as we go. Let's look at the thing. We need a multi-heap info type. So right here, let's say, actually, we can do it above here. And let's get the spacing of this right. Multi-heap info type. And we'll call it heap info. And then we'll pass in, it wants the heap info here, and it wants the caps, which is going to be this malloc cap 8-bit. And then Intellisense is a real helper. We can just hit a dot here, and it'll say, let's look at all the things we have available. Digits, current state, free blocks. It's not going to have all of this stuff on it, so let's go back to the documentation. And let's take a look at the multi-info. If we click on this, it'll show us, here are the things that we have. Total free bytes. So let's look at total free bytes and then largest free block. Total free bytes, largest free block. Total free bytes and heap dot largest free block. And let's do this. Let's do our log manager info. We'll call this memory. And then we'll give it, we'll say total free bytes %d. And we'll do the same thing. We'll say largest free block. The reason I didn't spell out block is so that they'll line up hopefully on the output and be a little bit easier to read, but we'll see how it goes. Yeah, okay. So let's do that. We'll call the get, and then we'll do what we've done before, vtask delay, and we'll do this every 3 seconds. 3,000 divided by v. I can't ever remember. It's down here. We'll cheat. Port tick period milliseconds. There we go. Okay. Okay, so we're going to say that that's our task. And now if we want to run that task, right down here, I'm going to get rid of this peace out stuff. I think I might come back to it actually. And then I'll just say log manager info main. And we'll just say launching memory task. And then the way we do that is x task create. And then there's a whole bunch of things, but the first thing it wants is the function, which is, what did I call it? Heap. I can't even remember what I call my function. Report heap memory. Report heap memory. And then the name we can give it is, I don't know, it doesn't matter, memory. Stack depth is how big of a stack we want to provide this. It doesn't need a big stack at all, so let's just try like 1024 bytes. And PV parameters, we don't want to pass anything to it, so I'm just saying null. That would be what actually gets passed in. And then the priority, there's a way to give it a default priority, which we'll come back to. So right now I'm just going to say null. And then the last thing is you can pass in a task handle, which then gives you the ability to like save a handle to the task that later on, if we want, we can call other FreeRTOS functions against. I'm going to say null because I'm not going to pass it in. Now let's come back to the docs and take a look at priority, because like I said, I believe there is I'm in memory still. A system, where was it? FreeRTOS. There's a way to call it with a default priority. Idle priority, which I believe is that default. So let's try that. you can use it as a number as well. Like the FreeRTOS scheduler will always try to run the code with the highest priority that's waiting to be run. And so you can order that however you'd like. But since we're just playing around, I think we can just use this idle priority. And let's just see if this will build, first of all. See if we haven't made some mistake. And we have, because we always do. It's going to say initializing argument 1 of cannot convert. Oh, it wants a pointer to that. I assumed it was, and so we just pass a reference to this. I should fix that. Okay, that looks like it's going to link for us. Great. Let's flash it, and what I would expect to happen is we're going to say launching memory task, and then our main task is done, which I think is fine. And then it should start reporting memory. So let's give it a shot, see what happens. What time is it? 30. All right. I wasn't paying attention. Did it? I'm gonna hit restart task. Okay, it's writing. Okay, and as I've said in past streams, when it does this, you've done something wrong. So I'm going to go ahead and unplug it and see why on earth I'm crashing over and over and over again. Multi-heap assert. So it doesn't like the code that I'm writing. So if we look here, pro CPU starting up, starting scheduler, and then corrupt heap detected. Why do we have a corrupt heap? That's a good question. Have I done something here that it does not like? I don't see how that would be. And then it doesn't seem to like how I'm calling that. And then it just reboots over and over and over and over. So just for kicks, this is why I'm doing this, because I need to understand more about how this stuff works. I'm going to, instead of logging it, we'll just get it without actually reporting it. It'll be build this again. Program it, and if it still bails out here, then I'm doing something else wrong. Okay. It seemed to do that just fine. It never did print out this. I wonder if, even though I'm creating a task, I wonder if it's somehow tied to the existing task and I need to keep it running. So let's do that. And now so what I just did was I uncommented that. So this our app main task will continue to run while letting the other tasks that we created. And I wouldn't expect that to be the behavior. I would expect X task create to spawn off another task that the scheduler handles independent of app main. But maybe there's a parent. Okay, so launching memory task, which I forgot. You always want to put a new line to make this stuff more readable. We'll do that up here as well. Okay, so the main task is running happily. So now let's uncomment one of these and see why it hates us. We got to restart the task there. And now if it starts barfing again, then it just doesn't like how I'm calling the heap caps get info. Huh. Oh, something happened there. Yeah, okay. Same thing. Panic. Panic. Interesting. Gives me a backtrace. So it's still crashing. Corrupt heap. I wonder if I'm just not giving it enough stack size. Is that a thing? So let's go 2048. I don't know. And now it's just crashing over and over and over. So these are the kind of things that you don't learn by just doing copy pasta code, because obviously their code's going to work, and I don't like just copy paste code over and over and over. So now look at this. So I gave it a little bit more stack, and it looks like things are working better now. So at least from where we were, it looks like we were just having a stack overflow. 1024 was not a big enough stack. I'm gonna let that run for a second. And this is why, by the way, I have this integer in here, because otherwise you wouldn't know, where you were. Or if I leave this screen and I come back and it had reset, I wouldn't know that. But now I'll see. If I come back and the number's less than 10, we've reset somehow. So let's look at internally within the FreeRTOS implementation, tasks use 2 blocks of memory. The first block is used to hold the task data structures. In this case, there should be none. Well, no, okay, the task data structures, yeah, the raw stuff from the FreeRTOS implementation. The second block is used by the task as its stack. Then both blocks of memory are automatically dynamically allocated inside the xtask create function. If a task is created, yeah, then okay, we're not doing that. Can only be used to create a task that has unrestricted access to the entire microcontroller memory map. Yeah, okay, that's fine. The size of the task on the right. Note that this differs from vanilla FreeRTOS, but it doesn't really give us any guidance. Like 1024 feels like a very large stack. A lot of bytes. But I don't have a really good understanding of what all is passed around. In bytes, not words, yeah. So I don't have a good understanding of how much resources a task requires. So like recommended FreeRTOS task stack size. Let's see if somebody's got like a, yes, like this guy, I tried to go 128. If you're using and cannot create the task after increasing its, then you're running out of. So let's see. This probably links to the FreeRTOS. Okay, the number of words. Oh, wait a minute. I was reading that backward. This says the stack size is specified in words, not bytes. Okay, so a byte is going to be a word is going to be 2 bytes. For example, if the stack size is 16 bits wide and the stack depth is 100, then 200 bytes will be allocated for use as yeah, because 16 bits is 2 bytes. As another example, if the stack is 32 bits wide and the stack depth is 400, then 1600 bytes will be allocated. Okay, so I was thinking it was bytes. It's not, it's words. And I believe, since this is an ESP32, that the stack is 32 bits wide. So we should actually that would be 4 bytes to a word. The stack depth multiplied by the stack width must not exceed the maximum value that can be obtained. Yeah, size type, yeah. So let's check out this FAQ of how big should the stack be. I'm a little worried because it seemed like that's bigger. So right now I'm saying that's 4, so 20, let's do a calculator. 2048 is what we changed it to. Times 4 means we're using like 8,000 bytes for the stack. Seems like a lot. And so exactly as when using a bare metal, the amount of stack required is dependent on the following application-specific parameters. And this is not anything new to me so far, which is the function called nesting depth. There is none. Like, we don't have nested function calls. It's just the one top-level loop. The number and size of function scope and variable declarations. Again, all we have is this multi-heap info type, which we could look at the size of. Okay, look, we still haven't crashed. That's a good check here. We're doing good there. And it doesn't look like the heap size is changing over time, which is also good. No memory leaks. And it looks like we have about 295K of RAM, which is pretty good. But back to this, all we have is that type. I wonder if our log manager, well, our log manager is declared up here. So that shouldn't really be an issue, but maybe it is. I bet it is. And I'll tell you why in a minute, but let's keep reading the number of function parameters, none. The process architecture, the compiler. The processor context is saved onto a task stack each time the scheduler temporarily stops running the task in order to run a different task. The saved processor context is then popped off the task stack the next time the task runs. Okay, so that I did not know. So every time it has to task switch, it's got to save the whole context of the task on the task's stack. That's a good thing to know. The stack space required to save the processor context is the only addition to a task stack requirements that comes from RTOS itself. That's good to know. Tuned, taking a pragmatic trial and error approach. UX task get stack high watermark API function can be used to see how much stack space has actually been used, allowing the stack size to be reduced if more was allocated than necessary. In addition, the stack usages of all the RTOS tasks can be viewed at once using the UX task get system state. Oh, I'm interested in that now. Okay. This is super helpful to me. I don't care about this. It's in words, not bytes. That's an important thing to know. Stack usage and stack overflow. Each stack maintains zone and dimension by a parameter passed to that. If a task, yeah, we know that already. FreeRTOS therefore provides two optional mechanisms that can be used to assist in the detection and correction of just such an occurrence. The option used is configured using the check for stack overflow configuration constant. Yeah, so this is what we were talking about earlier. It's likely that the stack will reach its greatest depth, deepest value after the RTOS kernel has swapped the task out of the running state because it's got to save all that context. And so I don't think I'm going to mess with that. I think we're going to go with this. Well, actually, yeah, this is interesting too. From raw data provided by, yeah. Cool. This is a way to use that. Make sure the right buffer does not contain a string. Get number of tasks, so that's cool. For each populated position in the task array, format the raw data as human readable ASCII. Runtime counter, stats as percentage. Cool. Okay. But the other one I wanted to see is this task get high watermark. They even provide you an example task. So we're gonna need, I don't like how they formatted this, but let's take it. This is not reset, so we were definitely apparently running over the stack size, and I really think I might. I'm not gonna like it. I think it has something to do with how we've done our log manager with var args. I'm worried about that being the case. So let's take this and let's take the high watermark here. Calling the function will have used some stack space. We would therefore now expect to return a value lower than it was called on entering the task. I don't fully understand that, but we'll leave it there. And then we want to call this inside. And I feel like we have to print it somehow. Stack high watermark. I don't know why it's not finding that variable. Oh, probably because of all this nonsense. I forgot the new line. I'm just going to make this really hard to read. All right, let's see where we end up here. Rogue Security, what's up? Thanks for joining. We're learning more about FreeRTOS tasks. I'm playing around with them because I have a knowledge gap and I'm trying to just play with different things and see how we end up here. Okay, so launching memory task. Right in here we say stack high watermark initial, and I'll have to look, is this in words or bytes? So that would explain, before we had it at 1024, so that's obviously a problem. Stack high watermark 324, 260, 260, 260, 260. So I don't understand. The value returned is the high watermark in words. Okay. 4 bytes of stack were unused. If the return value is 0, then the task has likely overflowed its stack. If the return value is close to 0, then the task has come close to overflowing its stack. Okay. So high watermark, to me, high watermark means like high watermark was like when you're testing like how high the water has come up on something, it'll leave a watermark. So even if it's come up and it's dropped down, like the watermark is how high it got. So like conceptually, I would think of high watermark being like how much stack space have we used, whereas this is more how much stack space is left. And so in words. So that is a little counterintuitive to me, just the way my brain works. So the initial high watermark was we had lots of stack space left, but now we're down to 260, which seems to be fairly constant. And so before, that makes total sense. We were trying to use 10, what was it, half of that, 1024 as our stack size right here. Right now we're doing 2048. 2048 seems to be what we need. Now, that seems like a lot, because remember, this is in words, so we're talking 8,000 bytes for our stack, which feels like a lot. Let's do, just for fun, log manager info. Let's print out size of let's put it in the task here. Size of heap info. Like, how big is this struct? Doesn't seem like it should be very big. So let's do this. Restart task. And see how big the... I think I'm going to also add on this last one. I know it's too late now, but a double new line. So that we get a little space in between all the printouts. Yeah, see, 28 bytes is not very big at all. And so why are we using 8,000 bytes for the stack? Well, not quite. 8,000 minus whatever, 260 times 4. Minus 1,000. So 7,000. We're somehow using 7,000 bytes on the stack. And I'm concerned that it's the log manager. So I'm going to comment these out. I don't... And just for fun, but the macros are going to have to do the same thing, but they're static. Let's just do this. Let's do a printf of the same thing. Of this. And then same thing down here. Let's just see if this makes any difference on our stack. Also, for kicks, let's see how big our log manager is. Size of log manager. Like, I need to understand why we need so much tasks, why we need so much stack space. I've forgotten a semicolon here. It's a lot of bytes, a lot of unaccounted bytes, unless that's just the standard, like, how task size that needs to go on the stack, in which case that will make me feel better. It's a lot, but it's not from my code. Size of log manager is 4 bytes. Yeah, I mean, okay, so we went from 748, which is what it was before, and now we've had 530. So we went from 260 to 532. That frees up quite a bit of space on the stack. So why does our log manager take up so much space? Oh, we're also not, well, to be fair, let's print all the things. Because all these strings shouldn't be on the stack. I mean, those should all be in other data areas. But let's make sure it's an apples to apples comparison. Okay. Okay. Same, well, 468. That's still pretty big. It was 260 before, so that's 200 words times 4. That's 800 bytes. 800 byte difference by not using the log manager. I can't explain that. I don't understand why there would be that much of a difference just by using my log manager, which is, again, not a very big object. Okay, let's take it one step further and let's include ESP, I believe it's log.h. And now, instead of printfing all of this, let's ESP log I, which I think I have to pass a tag like that. Let's do this. Oh, no, I don't want to do that. Escape. I want to start up here. And this should be more figured out at compile time. I don't know if we have to set the log level. So let's actually do E just to make sure it gets spit out. Log error. Okay. See what the stack size looks like now. Okay, stack. Huh, interesting. Stack high watermark is a little closer to that 260 than it was before. So, interesting. Why does the stack have to be... I'm going to have to really research this more and understand. So this is actually more comparable to my logger. And I that little bit of extra I'm willing to pay for the abstraction that I get from it. So very interesting. Okay. And one last thing I want to try, and then we'll end the stream because I think this has been really interesting. The next thing I wanted to do, and I'll play with off stream, is how does this relate if I want to wrap all of this in a C++ class? And I'll play with that. But what happens if we change this back to log manager? Well, okay, so we know where that is. That's about where we were. So let's just let's Control Z and change these back to printfs. And this back to a printf. And then let's comment those out. Get these back. And see what happens. So I don't know how to do this properly, but I think it was this parameter right here. What happens if we try and pass the log manager in? And then out here, I want to say we can do something like log manager. We'll just call it LM for now. Equals. We might have to like do a dynamic cast or something, but PV parameters, something like this, and then change these egg to just LMs. There's no way this builds. I give it a 0% chance. Okay, it built. Man, I really missed that. I'm going to give it a 0% chance that it's not going to crash. I don't know. Okay, let's try and actually flash it. What do we have to lose? It didn't like that. Come on. Flash and monitor. Restart task. So we're passing it in now, which really puts it on the stack. See, that's where this log manager shouldn't even be on the stack. So I would expect this to be worse. We're back to 260. So that made no difference whatsoever in our stack usage. Okay. Made no difference from our original. So our original initial stack, again, is 1748. That was pretty constant across all the tests. And then we're down to 260 when we use our log manager, whether we pass it in or whether we don't. And so I guess this is where my understanding is falling apart a little bit. Like, I wouldn't expect this to be on the stack. But I guess it has to be because it's context that this needs. So that does make sense. But again, why it requires so much more than a printf? I don't know. Okay, well, I'm going to call it. I'm going to call the stream for the day. Got to get through this because this is something, again, like I could copy paste code to get like functionality working, but I have to understand what's going on under the covers on this so that I don't hit an unexpected Stack Overflow when this is in the hands of a customer and it's like, I don't know, I was just copy and pasting code. Like I need to know, yeah, this is never going to overflow because I have allocated a big enough stack based on my perfect understanding of how big of a stack size we need. And right now I don't have that. Right now I have no idea how we're getting this 260 words left of our 2048 word stack size. And again, I believe we're dealing with a 32-bit stack since it's an ESP32. So we would multiply that number by 4 to get the size in bytes, but I don't understand that. So it obviously has to do with the context switching. So I need to understand more how to accurately predict and understand the size of the context that's going to be saved on the stack when we switch between tasks, because I will have several tasks running in the current design that I'm thinking of to see how all of this stuff works. So thanks, Bellum, Rogue Security, thank you for joining. Really appreciate having you. Hopefully this was somewhat helpful just to see me go through some of these exercises of trying to figure out the nuances and the nitty-gritty details of how the stack works with tasks and things like that so that we can have a better understanding of it moving forward. So thanks so much for watching. Hope everybody has an awesome rest of their evening. For me, I know some people are watching from 9 hours time zone, so it's like tomorrow there, but have a great rest of your day, whether it's morning or evening, and we'll see you next time. I don't know if I'll be here tomorrow, but if not, for sure Wednesday I should be back with more of the process. So thanks so much and have a great one.